Welcome back, associates. Today, we aren't just looking at raw data, we're looking at identity. In our previous sessions, we talked about making ghosts visible, but now we need to know exactly who those ghosts are. Imagine a world where everyone carried a universal ID card that records exactly how you would fall apart if hit by a high-velocity marble. In the world of molecules, this is the gold standard of identification. Have you ever wondered how a crime lab identifies a mysterious powder in minutes? They use the molecular fingerprint. Some fear electron ionization, or EI, because it's a hard ionization technique that breaks molecules. But the pro move is knowing that how something breaks is its most unique feature. This predictability is our ultimate asset. Today, we meet the veteran, electron ionization. Before we dive into the physics, let's look at the management briefing. We have several key KPIs to hit. First, the 70 eV standard. This isn't a random number. It's the universal currency of mass spectrometry that ensures data generated in London is identical to data from Tokyo. Second, we'll take a hardware tour of the filament, the repeller, and the electron trap. Third, we will witness the birth of the radicalcation, or M+, and understand the thermodynamic debt a molecule pays when hit by the beam. Finally, we'll learn how to leverage global libraries, like the NIST database, to turn a hit list into an instant identification. You aren't just running a machine, you are decoding the molecular world. Let's recall our previous audit in Module 5.1. We established that the mass spectrometer is blind to neutral molecules. We need that charge catalyst to turn ghosts into actionable data. We know hard ionization is like throwing a vase against a wall. Today, we learn how to measure those shards so accurately that we can reconstruct the original image every single time. To create a fingerprint, we need a hammer that hits with the same force every time. Without a standard hammer, we'd have a Tower of Babel situation where no lab understands another's data. That standard is our 70 eV electron beam. If we're going to use fragmentation as a fingerprint, we need a universal standard. That weight is exactly 70 eV. This is our executive standard. We'll look at the ionization efficiency curve, the performance chart of the source. We will see where the sweet spot lies and why increasing energy beyond this point offers diminishing returns. Reproducibility is the only currency that matters in a global market. If your data can't be reproduced by a regulator, it's worthless. 70 eV is the gold standard that makes our identifications bankable. Think of your molecule as a Lego set. If you throw a marble at it too slowly, below 15 eV, nothing happens. They stay neutral ghosts. As we increase energy to the 20 to 50 eV range, the number of ions produced climbs rapidly. But around 70 eV, the curve plateaus. This is the maximum efficiency for most organic molecules. Since most molecular bonds only need about 4 or 5 eV to break, hitting them with 70 eV provides a massive excess of energy. This ensures fragmentation is predictable and reproducible. Caffeine will break into the same pieces in New York as it does in Tokyo, turning chaos into a predictable digital signature. Let's look under the hood. The EI ion source is a masterpiece of rugged engineering, built for consistent, high-energy collisions. It is the engine room of your mass spectrometer. We will examine 4 critical components: the filament, the source of our electrons, the electron beam itself, the repeller or the bouncer of the system, and the trap, which ensures our beam stays steady. 80% of EI troubleshooting happens right here. If you understand these components, you can diagnose a failing system before it ruins your sample set. First, the filament, made of tungsten or rhenium, is the sun of our source. We pass a current through it, it heats up, and via thermionic emission, it emits a steady stream of electrons. This current is a critical management lever controlling how many electrons fly at our sample. These electrons are pulled across the chamber by an electric field, accelerated by a potential of 70 volts. They fly in a focused beam and intersect your vaporized analyte molecules at right angles. This orthogonal intersection in the ionization volume maximizes the probability of a high-energy collision. Then, there's the repeller. Think of it as the bouncer at the club. It's a plate with a positive charge sitting behind the ionization zone. Since like charges repel, the repeller pushes our positive ions toward the mass analyzer. Without it, ions would just drift and crash into the walls. On the opposite side, the trap catches unused electrons. By measuring the current at the trap, the system monitors beam stability. If the trap current fluctuates, your ionization efficiency and quantification are gone. Watch your trap current like a hawk. It is the heartbeat of your system. Now for the chemistry. What happens during that split-second collision? We witness the birth of a radical-cation, or M+. We'll look at the landmarks of a mass spectrum, the molecular ion peak, showing the weight of the intact molecule, the base peak, the tallest and most stable shard, and the daughter ions, which tell us about structural subunits. This is the CSI work. You are looking at the wreckage of a molecule and using it to reconstruct the blueprint of the original structure. When a high-energy electron passes near a neutral molecule, M, it doesn't usually stick. Instead, its field distorts the molecule's electron cloud so violently that a valence electron is ejected. This creates a radical-cation, M+. The formula is M plus an electron produces the radical-cation M++ plus 2 electrons. Because it's born with 70 eV of energy and only needs 5 to break, it's like a lottery winner who has no idea how to handle $70 million and starts spending recklessly. The molecule breaks its own bonds to shed that excess energy, creating a unique fragmentation pattern. In your spectrum, the molecular ion peak, or M+, tells you the exact molecular weight. If this peak is missing, your molecule was too fragile to survive its own birth. Next is the base peak, the most abundant fragment, which we set to 100% intensity. Finally, the daughter ions are the smaller pieces. By measuring their mass-to-charge ratio, we can identify specific functional groups, like a methyl group at 15 or a phenyl group at 77. This is the ID card that proves identity. Because we standardized 70 eV, every mass spectrum is a specific digital signature. This reproducibility allowed us to build the NIST library, the Google search of chemistry. When you run an unknown, the software performs a high-speed match against hundreds of thousands of compounds. Instead of spending weeks on structure analysis, EI gives you a hit list. It might say there is a 98.5% probability your molecule is ibuprofen. EI is non-selective. It identifies anything you can vaporize, making it the ultimate ghost hunter. Let's recap. 70 eV is our sweet spot for universal efficiency. The filament and repeller are the engines driving the process. Molecules become radical-cations before shattering into unique patterns. This pattern, matched against the NIST library, makes our identifications bankable. Reproducibility is the ultimate currency in science. You aren't just breaking molecules, you're decoding them. But sometimes, a molecule is so fragile that 70 eV turns it to dust, and we lose the molecular ion peak. In our next unit, the gentle touch, we leave the hammer behind and learn chemical ionization to keep even the most delicate molecules whole. I'll see you there.